Hello, welcome back to the discussion on the final exam solutions of Digital Systems and Computer Architecture course held in RV University. We are in the part 2 discussion where part A was discussed initially up to question 5 and question 6 was also touched upon. Now let us continue from where we left in the previous lecture. If you have not watched the part 1 part of the recording, please watch that before you continue with this. Now, we were discussing about how does this subsignal plays a role in complementing the second wave value, which is B, and then adding a 1 to it, because the same subsignal is coming here as a full adder input and it is going to be performing the addition here. 1 is getting added to the complement of the bit, then which is going to be added by the full adder circuits given here. Now, what is the reason why we use the same full adder circuit to perform the subtract operation? Let me explain. Now, this is a simplification of the digital circuits because we don't want to have another subtractive circuit in the computer. If suppose you want to perform a plus B, it's very straightforward. The subsignal will be made 0 and we perform the addition, because this XOR gate is not going to play any role because the subsignal is going to be 0. So whatever comes here will be given here, will be coming out, and this input is also will be 0. So it is perform as addition operation. Now in case I want to do a minus B operation, but I don't want to change the circuits which are given here. I don't want to replace it with a full subtractor. I want to perform a same subtract operation using the full adder. How can I do it? As long as if I perform a addition operation of the minus B that is given to me, then I will be able to perform the same addition. Now how do I get the minus B? Before adding a minus B to it, then I perform the same A minus B, right? So how do I find the minus B? I find the 2's complement. Now how do we get the 2's complement? We perform the complement of these bits, whatever is coming in, and then add a 1 to it, then we get a minus B value. So let me give an example. Now suppose if I have a value which is 0, 1, 0. I want to perform a minus 2 operation with A, whatever is 4-bit value. I want to perform a minus 2. Then I should first find the minus 2 and represent it in binary form. How do I do it? I find the 1's complement of this and add 1 to it. Now 1, 0, 1. I complement each bit and perform a addition operation which is 0, 0, 1, which is nothing but 1 is fed here. Then I get a value which is 0 here and one carry goes 1 and then 0. So I perform, let me write it here. Maybe the space is not enough for you. To understand it better, so let me remove everything. Now let me find the 2's complement of this value by first find 1's complement, then it will be 1, 0, 1, and then I need to add a 1 which is 0, carry is there, 1 and 1. So this is the value which represents minus 2. Now is it true? Is it really minus 2? You can verify it by finding another 2's complement of the same value. That will be 0, 0, 1 plus 1. It will get back, you will get back the original magnitude you started with. So remember, if the MSB is set, okay, if I am considering only 3-bit value, then if MSB is set, then it is a negative number. Then I find, if I want to know the magnitude of that value, I do the 2's complement and get the magnitude. And originally if I am starting with some number which needs to be represented in negative form, I do the 2's complement and get the value. Now whenever I perform a 2's complement, I will get the MSB set to indicate that it is a 2's complement representation of originally what I started with, and that gives me a clue that it's a negative number. So if I am interested in doing a negative operation, so I do a minus B, then perform an addition operation which is same as A minus B. So that's what is being done here for a subtract operation using the same full adder. Now let us go back to the question here. If the sub signal is circuit below is high, I am assuming that sub value signal is high, that means 1, then input B given to the full adders will be, is it same as the input values of B0 to B3? No, because if sub is 1, it's going to find the 1's complement. So it's not 2's complement, it's 1's complement. So it's a complement of the input. It's same as 1's complement. So complement means just you are complementing the input, which is same as 1's complement. So this is the correct answer. It's not going to be all ones, it's not going to be all zeros, because it depends on the value of B0 and B0 to B3. It's not independent of them. So B is the correct answer for question 6. Let us now go to question 7. It talks about a K-map, the number of sum terms in the minimized product of sums. Now, let us understand what is product of sums, and then we get into the discussion. Now, there are two ways you can actually get the expression, a simplified expression, given a given a K-map. Now, K-map actually for maybe some variables, it's not shown here, it doesn't matter. Now, there are two things, sum of product, product of sums. Now, sum of products. I am doing a sum of product terms. Product terms is AND operation, and sum is OR operation. That means this going to give me a circuit which is performing a AND operation of all the given terms and then perform a OR operation. Either I can represent it using AND followed by or product of sums. Now, what is product of sums? Product is come and internally sums of some terms are there. So I have this. In that case, I am performing an OR operation first on all the inputs, and then the second level is going to be AND operation. So it can be represented in any other form. Now, if you want to do that, then grouping of the values here will be different. Now, if you are doing a SOP, you will be grouping ones. That means I will group all these ones. All the ones should be taken care of, and then I say that this many the minimized expression will be got. Now, if I am doing a sum of products, then I need not be in this case. I don't have to consider the don't cares. Whereas if I am doing the other form, POS form, product of sum terms, then I need to consider zeros. In that case, I may be required to use the don't care. Now, let us erase all this, and now let us look at the terms which are product of sum form. That means I will be using the zeros. So all the zeros should be considered. So maybe I can do this one, because maximum I need to take care of the zeros, and then I can take care of this. In that case, I still don't consider this 0. So I need to have one more term, maybe like this. So maximum I consider the expressions, all zeros as well as the don't care. So in this case, I am using the don't cares because it helps me to get a better simplified term. Based on whether A, B or C, D, whatever variables are there, you will have expressions which you will learn when the Karnaugh map discussion happens. In this case, how many terms are going to be there? This one and this and this. So three are going to be there. Now let us look at the question. Let me keep this. Here, if I am doing a product of sums, now is it a product of sums? I told you that product of sums term is performing a sums first and then doing a product of sums. So that means I need to consider zeros. I need to group them. So as I have grouped it, I got 3 terms, okay, sum terms, okay. That means B is the correct answer here, okay. Now, as I told you, this course covers not only Boolean digital design and Boolean algebra, it also talks about little bit about transistors and diodes, because they are the basic building blocks of logic gates with which we are now constructing the logic circuits and expressions, whatever we get, Boolean expression, simplified expression, we constructed using those logic gates. Now, one small question on behavior of the transistor. Now, this transistor, what is shown here is a PNP type because the current is flowing into this, and then the circuit also shows the directions of the current. Now, you need to have awareness about the KCL, which is Kirchhoff's current law. If a point is there and then you are having some current flowing, let me call I1, I2 and I3. Now, whatever is coming in has to go out because there is no storage that can happen within the point, which is a basic, there is no rule, conservation of energy. So you, whatever comes in has to go out. So here I1 is coming in, that needs to go out as I2 plus I3. So this is the Kirchhoff's current law. Now the question here, relationship between current is being asked, and the transistor being a component which is cannot store any charges inside, though capacitance are there inside, but effectively whatever is coming in has to go out. So you can see that the current which is flowing in is IE and the currents which are going out is IB. So this can be the capital IE means that is a DC current which is biased with the DC voltages. So IE is coming in and IB plus IC is the current which are going out. So applying the simple KCL law, KCL to the transistor circuit will give you the relationship between the currents. So emitter current is equal to base current plus collector current. So let us see whether the expression which is matching with our value that we have got by applying a KCL. Now IE equal to IB plus IC. Yes. Now we have the first option itself is correct. As other things are all different. So it's not none of the above. It's A is the correct option. Now I am given a Boolean expression and then you are asked to find out which one it represents, okay, which expression it corresponds to. So let us just try to solve this by considering the inputs and the options given here. Now, what is this operator? This is a XOR operator, which you must be aware. XOR, or we'll write it as XOR or EOR. Okay. Now, XOR operation is what? 0, 1, 1, 0 will result in 1, whereas 0, 0 and 1, 1 will result in zeros. Now, on that top of it, AND operation is done. Here is not shown as a dot, so but that doesn't mean that it's not an AND operation, it's an AND operation, it's implicit. Okay. So on top of it, AND operation is done. So if this has to be a value of 1, then this should be 1 because AND operation, and this XOR operation should be 1. Okay. Now choose all these ones wherever ones are there. Okay. Now if I say, okay, if suppose you are assuming that this is the expression A, then I should have got the output as 1 only when A was 1. Now I got 1 here output, but A is happens to be 0. That means if I perform a with this having a 0 and whatever may be the value here, if I am doing an AND operation, I am not expected to have a 1 here. That means this expression is ruled out. Okay, this is how you try to solve this kind of a problem. So this A is ruled out. Now what about B? B or C? Now look at again. B is 1 here and then B is 1 here when this 1 is happening. Okay. Now you cannot conclude it because none of the above is also there, but at least can you rule out something else? Now you see here C is 0 here. If C is 0, whatever may be the other combination that happens, right? C is 0, I should get 1. Okay. I should not get 1, but I got a 1 here. That means C happens to be 0 here and I still get a 1. That means C is also not getting ANDed. Okay. So this option is also ruled out. Now you have to choose between these two. Okay, still the problem is not solved yet. So you need to choose between these two. So let me erase everything. Okay, because you have understood that A and C cannot be there, because I'm getting a value 1 when A is 0. I'm getting a value 1 as an output when C is 0. That means AND operation I am performing. So it can't be 0. So that is ruled out. But B is also not sure, because unless you have to make sure that it is not a none of the above option, because we have to see whether is B is really correct or not. Now if you need to know B is correct or not, you have to make sure that this is also 1, because we know that these two are 1 and B is also 1, so it is taken care of, one value is taken care of. But we need to say that A exclusive OR with C should be 1. That means what? A and C should be different. Okay, they cannot be same. Now let us see. In this case, C is 0 and A is 1. That means they are different. Then this XOR of this two input A and C will be giving me 1. Then 1 and 1 and it with 1. This is correct. Similarly, here this is different. Okay, A and C are different here also. They are not same. Then this also will be A XOR B will give me 1. So this is the correct answer. Okay, none of the above need not have to be chosen. So you need to logically go into analyzing the truth table and then understanding the expression and getting the result. Okay, so the question 9 is B. Now let us go and understand what is the last question of part A. Then I will stop and then we'll continue with another video lecture for part B question. Now what is the question here? Before I go here, let me explain. Give the Boolean expression of f. Okay, now I was asking you to from the truth table find out the Boolean expression. Now what is being asked here is, given a circuit, give me a Boolean expression, and in terms of A, B, C and D, no need to simplify. So you are not expected to simplify this, just to give an expression for this particular circuit. So let us try to write it down. Okay, now AB is given, so this is AB. Okay, one expression is having AB, one is coming, and I am performing a add OR operation. So let me perform a OR operation, because I am trying to find out F. So F is equal to, okay, this is AB, A dot B or AB. Now what is coming here? AB is getting complemented, so AB bar. AB bar is coming and C is coming, and what is the signal here? What will be the expression? It is, I can write it in AB bar. So let me put a parenthesis to be sure that it is a complete thing is taken care of. Even without that it's okay, but still for clarity purpose, AB bar is coming in and then is ANDed with C. So I can write it as C. So this expression is taken care of. Now let us look at this one. Now what is it getting? It is getting AB bar as an input again here. So anyway, this plus operation is done. So let me write a plus operation. Now let me write AB bar again, because those are the I'm always writing A, B followed by C and D. Now D is coming, it's getting complemented here. So D bar, and which is getting ANDed by this. So it is D bar. So if you write this expression, it is correct for this. Okay, that's the expression for this particular circuit. Now this ends our discussion on part A. Let us come back on another video with part B. See you again in a part 3 of this discussion. Bye bye.